Welcome back to The Explainer. Today, we are absolutely packed with good stuff. We're unpacking the core concepts from days 4 through 7 of the Networking Study Guide. So we're going to bridge that massive gap between basic packet transport all the way up to petabyte scale system design. Let's just dive right into the essential mechanisms that make massive internet applications actually work.
Here's our roadmap for today's Explainer. We're starting at the transport layer with TCP versus UDP, then we'll move into DNS resolution, tackle scaling from 0 to millions, and finally, validate those designs with some back-of-the-envelope math.
All right, let's hit section 1, transport layer, TCP versus UDP. So, to kick things off, let's explore a classic interview question that kind of challenges a very common instinct. Think about this. When would you actually choose a protocol that loses data? I mean, our first thought is usually that data loss is completely catastrophic, right? But in system design, well, that's not always true. There is really a stark contrast between our two main options here. You've got TCP, which acts as this reliable but kind of slow workhorse. It guarantees your data arrives in perfect order and strictly manages network congestion. But, that comes with some heavy overhead. That rock-solid reliability is exactly what you need for loading web pages over HTTP, where, let's face it, a missing piece of HTML breaks the entire site. But then you have UDP. UDP basically strips away all those rules for raw, unadulterated speed. It is fast, but it's unreliable and unordered. For live video streaming or online gaming, UDP is exactly what you want. You'd way rather just drop a late packet and move on, rather than wait around for a retransmission that causes this jarring, annoying gap in the audio. To really understand why TCP is slower, we have to look at how it actually starts a conversation. Before a single byte of actual application data can even be sent, TCP forces a three-way handshake. The client sends a SYN to request a connection, the server replies with a SYN ACK, and then finally the client confirms with an ACK. This mandatory back and forth, it requires a full round trip of latency, and that is exactly why TCP is inherently slower right out of the gate.
Moving right along to section 2, DNS resolution. You see, humans remember names, but routers need numbers. DNS acts as the Internet's distributed hierarchical phone book. It translates human-readable names like google.com into IP addresses like 142.250.80.36. Now, the absolute key takeaway here is the word distributed. DNS is not just one massive server sitting in a desert somewhere. No way. It's a globally distributed tree of servers that are constantly working together. So what actually happens when you type in a URL? Well, the query takes this very specific iterative journey. First, your machine checks its own browser and OS cache. If the address isn't there, it goes and asks your local resolver, which is usually run by your ISP. And this local resolver, it does all the heavy lifting for you. It asks a root server, which directs the query to a top-level domain, or TLD server. And finally, it queries the authoritative server to get the actual final IP address. Because the resolver does this whole iterative hunt, your laptop or phone gets to stay simple and just wait for the answer. Now, doing that entire 5-step lookup every single time you click a link, that would literally break the internet. And that is exactly why caching, controlled by TTL, or time to live, is so absolutely critical. A short TTL, say 60 seconds, allows for rapid IP changes, while a long TTL, like 24 hours, massively reduces network traffic. Actually, here's a handy trick for your next deployment. Lower your DNS TTL to 60 seconds a couple of days before a major website migration. This totally prevents users from getting stuck hitting stale IP addresses during the move. Then, once the dust settles, you can safely crank it back up. Okay, let's jump into section 3, scaling from 0 to millions.
Imagine our single server just went viral, and suddenly we need to handle massive immediate traffic. When traffic spikes like this, you basically have two choices. Vertical scaling, or scaling up, is just throwing money at the problem by buying a bigger server with way more CPU and RAM. It's a super easy first step because, hey, you don't have to change your code, but you will inevitably hit a hardware ceiling. To survive long-term, you absolutely have to use horizontal scaling. That means scaling out by adding more separate servers to share that heavy traffic load. But wait, if you have multiple servers, how do users even know which one to talk to? Enter the load balancer. It sits right in front of your server pool and distributes incoming traffic using algorithms like round robin. Networking-wise, it basically acts as a super high throughput NOT device.
It takes requests on a public IP, rewrites the destination, and forwards them to your back-end servers on private IPs. So it's completely hiding your internal infrastructure from the public internet. Pretty neat, right?
Now, once you scale out those web servers, your database almost always becomes the next bottleneck. So let's rapid fire through some essential back-end scaling tactics. First up, database replication. You split your traffic, sending all your data modifications to a primary database, while multiple replicas handle all the read queries. Second is caching. This means moving frequently accessed data into lightning-fast RAM to completely avoid slow mechanical disk lookups. And third, stateless architecture. You must move user sessions out of individual server memory and into an external cache. This guarantees that any one of your web servers can seamlessly handle any request from any user at any time. But here's a problem you literally cannot solve just by buying more servers. Why does a server in Sydney always feel slow from London, no matter how much bandwidth you buy? Well, it's an unavoidable physics problem. Data is limited by the speed of light in fiber optic cables. This propagation delay means that at the end of the day, distance is your ultimate enemy. The ultimate solution to this physics problem? The CDN, or Content Delivery Network. Instead of making a user in London wait for an image to travel all the way from an origin server in Sydney, which, by the way, takes about 170 milliseconds, a CDN caches that static asset on an edge node physically located right there in London. We shrink a massive global round trip down to just 1 millisecond. For static assets like videos and images, this is an absolute game changer for system performance. And that brings us to our final part, Section 4, back-of-the-envelope math. Okay, so we've built this incredible architecture, but now we actually need to prove it can handle the load. Having a cheat sheet of data sizes tied to powers of 2 is incredibly helpful for this. Just knowing that 2 to the 20th is a megabyte and 2 to the 50th is a petabyte, it lets you instantly do the mental math. You can figure out right away whether an application's storage needs can fit on a single relational database disk, or if you're going to immediately require a massive distributed object store. Similarly, internalizing raw latency numbers is honestly eye-opening. Hitting RAM takes about 100 nanoseconds, while a mechanical hard drive seek takes 10 milliseconds. I mean, think about that. Reading from RAM is roughly 100,000 times faster. And a cross-country network round trip, that's even slower at 40 milliseconds. These raw numbers mathematically prove exactly why we rely so heavily on caches and CDNs.
Whenever you're hit with an estimation problem, just follow this totally reliable 5-step framework. First, state your assumptions out loud. Next, calculate your average numbers per day. Then you always calculate peak traffic. That's usually 3 to 5 times your average, simply because internet traffic is incredibly bursty. From there, derive your required storage or bandwidth. And finally, perform a sanity check. Remember, getting the exact, precise final number doesn't matter nearly as much as just showing your methodical, logical thinking.
Let's actually walk through a massive real-world scale problem together right now. Imagine we are designing a global video platform, something like YouTube. We'll assume 600 million daily active users. On average, let's say they watch 30 minutes of 720p video a day, which streams at about 4 megabits per second. If you calculate the concurrent viewers at peak hours based on those exact assumptions, we can figure out the total required bandwidth. And the mathematical result? It is absolutely staggering. At peak hours, this platform would require 150 million megabits per second. That's 150 terabits per second of bandwidth. This single number vividly drives home why serving all video from a single origin server or even a single data center is just physically impossible. You would instantly saturate literally every network link available. But hey, this isn't just theoretical math. Think about this. Netflix alone accounts for roughly 15% of all global internet traffic at peak hours. Tying our bandwidth math directly back to real-world infrastructure proves exactly why tech giants spend absolute fortunes on global CDN contracts. They literally have to push that data out to the network edge, or the internet would simply collapse under the weight of it. So to wrap up our explainer today, I really want to leave you with a provocative question to chew on. If you had to scale a system from 0 to a petabyte tomorrow, based on everything we've unpacked today, what is the very first bottleneck you would hit? Would your TCP handshake slow you down? Would your single database catch fire? Or would you hit a physical limit in propagation delay? Think about how all these layers interlock, and you'll be more than ready to design your next big system. Thanks for exploring this with me.